Good evening, everyone. I warmly welcome you all to the fourth day of Robotics webinar series organized by the IEEE Robotic and Automation Society of University of Peradeniya. The main purpose of this webinar series is to provide you with the fundamental knowledge on the robotic and automation. Yesterday, we talked about the fundamentals of designing a robot using Webots simulation software. So today, as the second day of the robot simulation workshop, we'll talk about robot coding and algorithms, simulate them using Webots software. With that, let me introduce you to the keynote speaker of today's session, Mr. Uddula Ranasinghe, currently an undergraduate in the Department of Electrical and Electronic Engineering, University of Peradeniya. He is an all-rounder student who performs in academics, sports, and extracurricular. He has experience in working with embedded systems, Arduino, and robotics, along with his knowledge in Weber simulation, Python, and other programming languages, circuit designing, machine learning, and neural networks. He has taken part in several robotic and innovation competitions and recently became one of the top 10 finalists of South Asia InnoChamps competition organized by Synopsys. He is also the secretary of IEEE Robotic and Automation Society of University of Peradeniya. He will be conducting today's session on Weber simulation, and we hope you all will get the best out of today's session. Before handing over the session to our speaker, I have a little announcement to be made for the participants. We will display a link in the chat box, and through that link, you can direct your question to us so that we will make sure to answer them at the Q&A session in the end. And also make sure to fill the feedback form from the session after the session. We'll send the Weber simulation files and the presentation to the ones who filled the feedback form. So without further delay, I would like to invite Mr. Uddula Ranasinghe to proceed with today's webinar. Over to you, Aya.
Okay, thank you, Ishmi. So good evening, everyone. Okay, today we are going to continue the work we have done yesterday. Yesterday we designed using the board. We designed some robots, and we created some solid objects, then movable and non-movable, and then we started to create our differential with robot. And hopefully today we are going to finish with creating the algorithm and other parts. Algorithm, sensor part. Now we have sensor part, algorithm part, and today we are going to use Python language. So let's go to the session. So let me share my screen. So okay. Yes. So if I summarize the work we have done yesterday, first we design. We talk about flowcharts, how they help us to create the Webot, how they help us in Webot environment, and how they help when we are creating project or any other design, how they make easier planning and designing. And I introduced you to an online diagram making software called App Diagrams, and then we move to the class diagram, flowchart diagrams. Basically, in Webots, we are using this simulation software to connect the nodes that we are creating together and run the simulation. So in Webots, what's really happening is we have nodes called robot node and wheels on the wheels node and sensors on the sensor node, and the simulation platform will connect these nodes together and run the simulation like the real world. So then today we are going to add sensor part to the robot, and then I will spend my time greatly to explain some algorithms. And today algorithm using Python, and I will explain it line by line. Maybe yesterday some guys asked some question. Hopefully, I will give some answers to them as well. Then this is our final design. This is our robot, and this is the our flowchart diagram, full flowchart diagram. Now we are at the state of this sensor part. We add our physics, children of hinge joints and body shapes. So now we are at the sensor part. So we talk about two-wheel differential robots. Basically, they are very low. They are low cost and simplicity and easy to model using mathematics. So we use it as our design two-wheel robot. So and today we are going to program the robot in order to control in our environment. And sorry, we design wheels, two wheels, motor, chassis, and the steel board. So now, how to use sensors? I think, yeah. I think the organizing committee has shared you a document including the Webot file. The file contains the environment and the robot, full robot, and the full code as well. You can download it and run in your computer. Maybe you can download it later and play around it and get familiar with the software and the environment as well. So how to use sensors? In here we are going to use IR sensors to get the values from the environment, to get the distance from the obstacles in the environment. And in Webots, usually the sonar type devices, that means the devices that measure the distance using any type of ultrasonic or IR or rays. As examples, IR sensors and ultrasonic sensors and even laser sensors are under this category. So we are going to model these sensors using distance sensor node, and then we will change some parameters to our in order to gain some value of the environment. Then we are going to use front, right, and left sensors. Maybe there are some advantages and disadvantages. We'll talk about that as well. So then a special point is maximum distance that these sensors in Webots are capable to measure is 10 centimeters. So we have that is the limit. Then this sensor is, okay, I will show this. Then if I talk about the languages, actually Webot is a pretty good capable of running many languages. As example, Webot is capable of running Python, Java, MATLAB, and ROS. Also, Webot directly come with inbuilt C and C++ compilers. So if I talk about languages, I highly encourage you to use C and C++ when you are especially planning to go towards embedded engineering or robotics engineering areas, because actually Python is good. We have a lot of libraries, we have a lot of support in the internet. So Python is kind of towards the data science and data analysis. Actually, this is my personal idea. Data analysis area. So Java is mainly focusing on web development and web-based application. MATLAB is pretty good at handling matrices, and we can, if we are going to do matrix calculations, we can use MATLAB. Especially this ROS is robotic oriented system language. This is specially for robotics. So if you are like to learn robotics, this is a pretty good language to learn. And why this? I recommend ROS and C++ to use program your robotics. C++, and ROS are mainly focused on the hardware part. The language is very near to hardware implementation. So we can control our hardware parts using C and C++. Even actually the running time is very fast compared to Python and MATLAB. So I encourage you to use Python, C++, but today, since many of you guys familiar with Python, and because it is nowadays Python is very popular language, so I'll be using Python to program today's session. Today our Go mobile robot. So actually, these are something about. So there are we in Webots we have a window call controller. I explained this thing yesterday. So deeply today we can write our program in this controller and any language using our previously mentioned language. We can write the controller code, and the controller code will control our robot. So in C language, if I talk about C++, we have to call a library called Webot robot. This is a API of the robot. This API is used to ask the called robot data. Details about the robot. Details mean the API is the place where all the data is available, and we want to import Webot motor library. This library is mainly used to control motors, and we want to import library called sensor. Sensor library is used to read sensors and go to get our readings. So, but you will see Python, we don't need to import any of these libraries. We only have to use a one library called robot, but it is easy, but it is come with some cost. The cost is Python is run from line to line. So when we compiling the code, Python will only compile the next running code line. So that means if we let's say we made mistake in line 50. So some part we made a mistake, but we can only identify this error only if the compiler when compiler run this program. So if I talk about the very large applications in the industry level, they contain sometimes thousands of lines of code. So what happened is when we have thousands line codes, finding errors using Python is very hard. But the C++ and other languages, they compile the whole code together, and so they will show us the errors we are having in any code. So actually, they are the mistakes we done by not the mistakes that logic errors, the mistakes done by us. Let's say we forget to type some semicolon, so those kind of errors. So with that, the algorithm. Today we are going to use the algorithm called potential field algorithm. Potential field algorithm. This algorithm is like it's actually, if I explain it to you, think about robot as a positive charge, and the obstacle we want to avoid as positive charges as well. So what happens is when this positive charge starting to move, these same positive charge obstacles will repel the robot, and the target, if we take the target as negative charge, eventually the robot will go towards the target, because it attracts the positive charge. This is a negative charge, and the positive charge will repel from this obstacle. So eventually, maybe this robot will take a path like this, and finally go to the target. So these are the algorithms. Today we are going to use this algorithm without the target. So you can, when you are coding, you can use you can code the target as well if you want. And there are other algorithms called fixed zona method and quadri method. So you can use them as well. So let's talk about the Python language. I talk the advantages. The Python is very versatile. It is versatile and flexible, and coding is very easy. We have large global community as well. So disadvantages are slow. Sometimes Python is slow compared to other languages, and also line by line SQL. I explain these things. So today, if I explain the algorithm that today we are going to use, is this is our robot. So let's add some sensors like this, and let's come back to this presentation and I will explain them. So sure. So share again. I hope you can see the screen. This was our arena, and this was a solid box, wooden box, and this is a sphere. So now we are going to and we created this robot named GoMobile. So this is our scenery, and okay, I will show you how to add these sensors. So now I have a robot that I added these sensors before coming to the session, because to time saving purposes. So I will delete one sensor and I will add it from the beginning. So let's go to under our robot nodes. Now give me a minute. Under the robot node, go to this node called children. I think I explained these things yesterday. So today I'm going to speed up a little bit. So let's delete the front sensor. So now what I'm going to do is I'm going to add this front sensor from the scratch. So in order to design the front sensor, under children node, go to this add icon. Then what I want to add is a distance sensor. So go to this under base node, go to this node called distance sensor. You can see here we have displays, compass, and cameras. Anything you want, GPS sensors as well. So today I'm going to use this distance sensor thing. So now we have a distance sensor. So let us name it as front sensor. So since this is not a definition, I am going to use simple case. So let's drag this open, and now we want to add a shape to our sensor. Go to the children node, add and on this children node, add the shape. First we need to add the shape for our sensor. Here you have shape. So today I'm mainly focusing on the coding part. So under shapes, let's add a geometry. Double click on this and you will get this pop-up window. So let's use a box shape. Add. So now we need to change the size of this sensor. I'm going to use this predefined size. I'm going to use this size, 5 millimeters in x-axis, 5 millimeters in y-axis, and z-axis I'm going to use 1 centimeter. So now you can't see the sensor because it is in this chassis. So we want to translate this sensor to this place, and in order to translate this sensor, so let's add the appearance as well. I'm going to add PBR appearance, and under PBR appearance, white color is fine with me. So roughness fine, and I want a non-metal sensor. So I'm going to change the metalness to 0. So now we have a non-metal sensor. So what I'm going to do is I'm going to translate this sensor to here. So first of all, I will translate this sensor onto the chassis. So go to this under this front sensor node. Go to this translation node. So I'm going to translate on Y direction RGB for XYZ. So I'm going to translate 7 millimeters. So now you can see the sensor. So in distance sensors, the main part is the sensor is taking value only in the x-axis. So this this sensor takes the values positive as in x direction. So we need to rotate this sensor into the front direction in order to take the values from front side. So to rotate this, I'm going to go this rotation node, take the rotation axis as Y. Then I'll rotate the sensor. Actually need to rotate 5/2 radians. It is like 1.5527. So now you can see sensor is in front direction. So and I'm going to translate this to this point. So again I'm going to this translation. So let's change the direction Y direction in 0.4 centimeters. So as you can see, now we have the sensor. Similarly, we can copy and paste, copy this sensor using Control C and paste to another sensors like we did in our solid and in wheels. When we are adding wheels, we did that technique. So So similarly, you can add this other sensors as well. I would maybe sometimes you may have the file with you as well. You can open that if you want. So now we have uh, 3 sensors. So I'm going to save this. So last day I told you you can save using this, and there is another method. You can use this button to save. So I'm going to use that. So now we have saved file. So okay, now what we need to do is we need to write the controller code. Controller code is mainly, let me open that. So let us build our controller. So today we are going to use language called Python. So in order to build your controller, go to this wizard icon and select this new robot controller. So there you get this pop-up window. Next, and choose the language preferences. I'm going to use Python. So let's put a name here. So let's put my controller 4. Yes, I'm very bad at naming things. So next, so click this open and finish. So now you are getting this kind of window here. So I will be maximizing this for you to see better. So okay, maybe I will. Okay, I will give this answers. So first I delete this part. So okay, first what you need to do is when you are designing your robot control part, first you need to get access to the robot. To get access to the robot, in Webot we have a library called controller. So from the controller library, that means from the controller library, we import the part called robot. So robot means this node. This robot means this robot node. So we are importing the robot node from the Webot controller. I think you understand that. So then in Webots, we have a variable called timestep. Timestep mean, let me create that. So when you are defining things that will never change in the code, define them using capital letters. It is good coding practice. So timestep is actually it is a number. We can use 16, 32 or 64. So what this timestep mean is the step time. Actually this is when this time step value is higher, the higher the value, it is very much similar to the real world. Lower the value, it is more towards the simulation part, simulation world. But the cost we are facing is when you are increasing the time step number, the computational cost we need is very high. But when you are decreasing, the computational cost, the Webot need is very small. So today I'm going to use the time step as 64, and then I'm going to delete this. So this is another method you can get the time step. So then I am going to get a robot. I'm going to call this robot function from this controller. So I'm going to create a variable called and calling this robot function. So now simply by calling this robot, I can talk with the robot node of the simulation. So let's Here, this time step, I'm going to change our define time step. Time step. Okay. Now, what will happen is, I'll do something like this. So first, this is a while code. I believe, I hope, I think you are somewhat familiar with the Python language. You don't need to be very much familiar with the language. I will explain the things for the beginner level, but I think knowing something does not hurt. Okay, so first I'm going to give a tab. So let me actually this part is no need, but this is a good practice. So first I'm going to create name. So I'm going to create a function, one time running function in my code. One time means this code only runs only one time when the program runs from this line 1 to the last line. So this I'm calling this. It's very hard to program this text. Okay, now this is our one-time function. This one-time function is going to execute from line 17 to line 30. So in my one-time function, I have a loop. Here, when this is executing, I'm going through this while loop and going to run this over and over again. So first, so let's what I'm going to do is I'm going to delete this. So first, what you need to do is you using the robot API, you need to call these motors. The name you need to call the motors. So when I write this program, you will understand the theory behind this, and I will explain as well. So first I need a write mode, right? So let me create a variable called write mode, and this variable represent our write mode. So and obviously you are correct. We need left mode. So how to assign this variable to this road wheel? So let me create this. So in Webots, how we assign these motors is simply type in robot dot get device. I think my spelling is correct. Get device, and under this between this parentheses, you have to give the name. So you may remember we gave our names. We gave names to devices as motor L and other as motor R. So let me create code that for right motor I am going to create code motor R. For the left motor, robot get device. Name is motor L. So now we have access to the motors. So and to get the access for the sensor, so I will name this comment this configure motors, and Then I'm going to configure our sensors. Configure sensors. I will what? Okay. So in order to configure sensors, first we need to name our sensor. So this is our file we created under this front distance sensor node. You can see name. So here I'm going to change the name as front sensor. So since this is our front sensor, front sensor sync, okay, and then the legs. This is right sensor. Name is right sensor, and the left sensor name is left sensor. So in order to get the device, get access to these sensors, I'm going to name these sensors as front, right, and left. So let's get access to this our sensor. So it is similarly, it's similar to the robot motor robot. Get device. Our sensor's name is front sensor. And similarly, I'm going to copy this and paste here. Our right sensor's name is right sensor, and left sensor is left sensor. So now we have access to the sensor. So so now what I'm going to do is I'm going to save this text file. You can go to this icon here called save the current text file. I'm going to save this, and now what I want to do is I want to take this controller file as the controller of this robot. To do that, to do this, what I'm going to do is under this robot node, you have a node called this controller. Double click on this, and I'm going to select the controller code. Name is controller 4. Okay, and then press OK. Now the robot is connected to this controller code. So I'm save this file, and let's clear console, and let's run this and see whether there are errors or any other. So seems to be there are no errors, and the process crash sometimes also. Okay, this is due to we haven't finished our code yet, so I think there are no errors. So I'll clear this console. So now we have access to the motor. So in order to control this motor, next what we need to do is we need to specify the position. Position means let's think about right motor. So now what we are going to do is we are going to rotate this our right motor over and over until this robot is going to collide with something. So think about something situation like this. So you need to turn our robot wheel to some position, to any position. Let's say 2 rounds. So in that case, you need to specify that position. So in this case, since I'm going to rotate this wheel infinitely long time, maybe not infinitely long time, but I don't have any clue about the position. So what I'm going to do is under this motor configuration part, I'm going to set the position of the sensors motor as infinity. So motor and also the left motor. So I'm calling this motor, and I'm going to set the position to infinity. So how we do that? So right motor dot, this is the method you use when you are using Python. Right motor dot set position to infinity. How you define infinity in Python? Define infinity using float and underscore infinity. So similarly, what I'm going to do is I'm going to copy this and paste. So now the position is set to infinity. Then we are ready to go. But sometimes when we are starting our robot, maybe robot start to drive. Maybe robot, as soon as we start the program, sometimes robot may start to run. So to prevent that, what I'm going to prevent that situation by like this. So right motor, I'm setting the velocity to 0. Velocity to 0. It is better when if you can define these velocities in floating point. Floating point means this dimension 0.0, and I'm going to set this as left. So now we get access to our robot motors using this part, and then create the position of the sensors to infinity. Then now then we created set the velocity to 0. So now the motor configuration part is finished. So next we need to configure our sensors. To configure sensors, you need after you getting the access to the sensors. What you need to do is you have to enable these sensors. It's like switching on your sensors. To switch on, I use front dot enable. When enabling your sensors, you need to give the time step value as well. So I think spellings are correct. If I make a spelling mistake, let me know. So I'm going to enable front sensor and right sensor and our left sensor as well. So I'm going to save this, and let's just run and see. Okay, now we are getting error message calling. Here you can see at line 22. I do this intentionally. So at line 22, you see in Python you have to run the code in order to get the errors, right? So you see in line 22 there is error, this error. So if I go to line 2, you can see left is defined wrong, double T. So I'm correcting this, I'm saving this. Let's save this. So now our code is running correctly. So I'm again clear console. So okay, now we have access to our motors and sensors. Now what we want to do is we want to control. So what I'm going to do is let us give some velocity values to our motors, and let's see what happens. So, and one point is the maximum velocity that you can give to a motor here is 10, and minimum is -10. So actually this 10 means not the velocity, it means the radian velocity. That means the number of radians that it will rotate under a second. So in order to give velocities, same as this code, what I'm going to do is I'm going to copy this and paste this. So, let me comment this. Setting up the velocities. Okay, so let us set the velocities 5. Why not? Why not 5? So I am setting the velocities of both velocities to 5. Let's see what happens. Save this, click this, run this. Oh shit, bam. So our robot is moving backward, right? So can you think of a method that we can handle this? So when designing, we put our robots motors in backwards. So how can we do it? So in order to deal with this, first I'm going to create a session part called variables, maybe global variables. Global variables means variables that are used in every part of the code. These are valid for any part of this code. So I'm going to create a variable code. Let me create speed R for right motor speed. Let's set this to 5. And similarly, speed L 5. So this variable I'm going to use the speed. This variable as speed R, and then similarly here. I think you are understanding this. So now our robot is going backwards. To prevent this, what I'm going to do is I'm going to multiply this value by -1. Let's see what will happen. And save the code. Click here. Okay. Now our robot is perfectly fine. It is running perfectly fine. So now it can go straight lines. So now so what will happen if I create this speed L and this, let me copy this part, and in this I am pasting this. What I'm going to do is I'm going to change the left side speed to -5. Let's see what will happen then. So you can see when I'm changing the left side speed to -5, the robot is turning to left side. If I do the otherwise, I'm changing this to positive value and R value to positive, right side value and left value to negative. It will turn right side. It will take a right turn. So by changing this the sign of this speed, we can change the direction of rotation. So now what we need to do is I'm going to mathematically handle this thing, right? So let me comment out this. So let see how we can read sensors. So read sensors. So I'm going to use value L to left side value R to right side value F to right front value. So we can read the values using the command part is to read left sensor, you type left dot get value, and read the front sensor, what you need to do is right sensor, right get value. And to read the front sensor, what you need to do is front get value. So now you have values. Let's print this value and let's see what will happen. So in Python we print values using print command. I'm going to print value I'm going to print value L. Then after comma I will going to print value front value. You can see I am printing in such a way that left value is in left side, front value is at the middle, and right value is at right side. So so I need some space between these things. So let's create a space. So you can create space like this. So let's run this, and so you can see there are values. We can see values. So what I will show you, what I'm going to do is I'm going to grab this solid by pressing shift key and the left click. So when I'm going towards the left sensor, you can see the value is changing from the 1000 to the 0 value. So front side you can see middle value is changing, and left side, right side, you can see the right value is changing. So just like that you can get values and print. So let me stop this code beginning. So the many of you have a problem when we are starting to program using languages, I mean the computer languages. But the main problem we have is, okay, now I have this problem. How to model this problem using these languages? So what I'm going to do is I'm going to show you how to model these sensor values as an array. So in Python, what I'm going to do is I'm going to create an array containing values that if something is something is detected by this left sensor, some value is going to change. So it's like this wall. So I'm going to tell array called wall. In Python you create arrays like this. What I'm going to do is if my left value is less than 800, so it is from 0 to 1000. What I'm going to do is if it is less than 800, this statement is true. So you will see what will happen, and when I will print this array and show you. So what I will do is this is for R and this is for front. Then I'm going to print this wall array. Let's see. So now you can see again I'm going to get this. Now it is false because any sensor can't feel any wall, so it's saying false. So now the right sensor can feel a wall. It is true. If I left sensor, true, and front, true. So this is how we model some practical environment to a mathematical model. So here what I did was I modeled the presenting a wall in left side or front side or right side to a matrix called ball, actually array called ball. This array represent values, Boolean array. This Boolean array represent whether there is a wall or not. So I'm going to do this. So let us create a driver. So I'm going to create a driver called driver. Okay, driver means maybe you can think of it as a uh, uh, human driver or a file driver. Computers we are using human driver. So, and I'm going to create a driver, and I'm going to give this driver access to these walls. So it's like this. If we think about this as a driver, human driver, this driver is looking at the left. He is looking at. He is thinking whether there are walls in right side or front side or left side. So in order to create this driver, I'm going to create a function called driver in Python. You can create functions using functions. I'm going to create here a function using definition. Define a function. I'm going to use the name driver, and driver have access to this walls array. I'm going to name it as a wall. So, and finally return. This is how the program works, right? So what I will do is, after that I will print this array. Let's see what will this driver do. So I say this, I'm ordering this driver when we getting the array, print the array. So let's run this and see. Similarly, the driver get access to this wall array, and he is printing these values. So now what I'm going to do is, so now think you are a driver. So what will you do? So you are getting, you look at the right side and left side and front side, and then you are going to take some action. So what will happen is, if we think talk about this array represent this first element represent the left wall, this front wall, and this represent right wall. So to call a element, we can call element in Python using this this method. Our array name is arr. So if I press is 0, this is left hand. So what? So let's build the driver. So this driver is looking forward. Okay. So he look in the forward direction. So this driver, what will this driver do it? If this driver sends the front wall in this part, this driver will say us, okay, wall ahead, okay, and else what he is going to do is, else he is printing what, it's a go straight. So I think spelling correct. So go straight, and let's see what will happen. So save this, run this. So now here should be G. Okay. Now the driver don't see any wall in front of him. Now what I'm going to do is, I'm going to place this in. Now he is now what driver saying is, okay, wall ahead. Now you can see, right? So if I remove this wall, you can see go ahead and now wall ahead. So okay, now let's stop this. So what will do when there is a what driver going to do when there is wall ahead? Think about it. So when there is a wall ahead, what this driver do is he will look at the left side. So let's see the left side. How are we going to see the left side? So this is mathematical modeling. I think you understand this. So he is going to look at the left side, and then what he is going to do is he is going to look at the right side. So right side is this element, second element, right? So and then if there is a wall ahead and there is a wall in left side. So what is the thing we can do? We can turn our robot. So there is a wall in left side. What we are going to do? We turn our robot to right side. And if there is a wall in the head and a wall in left side, what we are going to do is turn left. So let's see how this our driver works. Yeah, now we can see drivers tell us driver still say go ahead. So okay, now I can't simulate this thing. So let's say name again. Okay, what I'm going to do, I'm going to close this and I'm going to create place. So I'm going to okay, I'm going to get two boxes and place them in this manner, and I'm going to put my robot like here. So now robots driver sees a wall ahead and wall right. Save this. Let's see what is the driver's output. So driver saying turn left. So what if we rotate our drive? Now he can see a wall ahead and wall right. So driver says turn right. So now I think our driver is working fine. So let's drop this and let's program. So I'm going to use this driver as a returning driver. Okay, this driver return the thing we need to do when we arrive to this portion. So what I'm going to do is instead of printing, this driver will return his value. So return. Okay, you will see what this return function do is. I will show you. Return. Okay, this driver next. Okay, what if okay, there is a possibility that drivers see. Then we see that, right? We saw that when driver see a wall ahead and he don't see any wall in left side or right side. So to address that case, what I will do is else if he don't see anything, he returns okay, space here. Okay, space here as well. He returns you need to do something. Okay. Okay, now it is fine. So then also I'm going to change this print to return. Maybe boring. So, and this return is unnecessary. I'm going to set. So this return function do is, so we can get driver's decision. Diverse decisions, and as like this, and print. I can print the decision here. I am covering the Python language as well. Huh? That is what this takes some time. Okay, now you can see driver is sending go straight. Now if I change to this side, the driver said turn left, and if I rotate this, driver said turn right, and okay, I think it is fine. So now our driver is working fine. So let's do something. So what if this driver, okay, according to driver's decision, we are going to change the wheel speed. Okay, so how we can change wheel speed? So driver giving us a decision. What we're going to do is I going to if driver says okay, driver's decision. I'm going to get like this. I think spellings. If I make any spelling mistakes, please let me know. Huh? Okay, if driver says go straight, go straight. So go straight. If driver says go straight. So what will we do if driver says if driver's decision is turn right? Turn right. Okay, goes to the C language, and here if driver's decision is okay, turn left. Why not? Turn left. Driver says now okay again. So driver, what will we do? So now if driver says go straight, we will make the speed of our rotating speed of our wheels. Okay, how we can change the speed? Sorry, the capital letters. Caps lock. Left tab. Left tab. Okay, here if driver says this, so change our speed to let's say 8.0. We go straight. Speed L to 8.0. So to in order to turn right side, we saw that control V. We need to set the right side value as a negative value. So 8, I'm going to use 5. I think this will work. In order to turn right, yeah. In order to turn left, same as this. I'm going to change the left side value as negative value. So this is 5. So let's see. Driver goes straight. Okay, we put driver here. Okay, what happened was I commented out the speed thing, right? Yeah, driver turning right? Okay, and drive is running, right? And let's put the driver here. The driver goes straight, and there's wall ahead. And driver turning. Right. So in placing this inside this wire. Okay, let's again run this. And then driver go away. Okay, let's see. Let's place driver here. What? Let's see what will he do. Okay, driver goes straight and he detect the right wall and let roll ahead. And he now you can see, as you can see. So what I'm going to do is now I'm going to copy this and paste another wall here. Let's see what we will do. Fine. I'm going to save this and I'm going to get our driver here and let's run this. Okay, driver goes straight and he detect a wall ahead and wall right, and what driver doing is, okay, let's print the driver's decision. It will help us. Okay. Driver said go straight, go straight, go straight. Now driver said still go straight, and now I want to run to. In order to run step by step, you can use this button. Okay, step, still straight, and driver says turn left. Okay, turn left. Now again, what driver says is go straight and turn left. And then now what driver says go straight, but still robot is not in a good position to go straight. So it's go through this wall and then try to go like that. So what I'm going to do is we need to control that as well, right? So let's check whether the drivers get the decisions. Rotate this like this, and let's put the robot here and driver to drive. Okay, driver say go straight, and then return left. And somehow, what happening here is driver don't see a wall ahead, so he said go straight. But still, the robot is not in a correct orientation to go straight. So we need to deal that thing as well. So how to deal these things? So as you can see, if I print these values, okay, other than I will print this again, these sensor values. So and again I am setting these velocities to work because I want robot control, right? So now you can see when this robot is moving towards the right side wall, right side value is going to be lower value, and similarly left side value is going to be lower when it is moving towards the left side. So what I'm going to do is I'm going to introduce another variable called here. I'm going to introduce another variable called error. This equals to value r minus, value r minus value left. Let's print this value, this error value, and let's see what this value means. Print So let's print this value, maybe. Okay, now it is 0. So if there is no wheel, no ball, is printing 0. And if there is ball in right side, is printing a negative value. If there is a ball in left side, is printing a positive value. So I'm going to use this negative and positive values to create something that can handle that the straight movement. Okay. So what I'm going to do is when driver says go straight, I'm going to do it. We saw that when the robot is more towards the left side, this value is positive. So if there is a ball towards the left side, what we need to do is we slightly increase the rotating speed of left side. Um, uh, left side motor, and let's slightly decrease the speed of right side motor. So let's remove error value from left side. We need to lower the value of right side, right? So we will remove some error value from right side rotation speed and add this value. But you can see this error value is in 0 to 1000 range. But our motor can handle only values from 0 to 10. So in order to map this 0 to 1000 value to 0 to 10 values, what I'm going to do is I'm going to multiply this value from a constant value, and I'm going to create this under variables KP. Actually, this is called a proportional controller. Actually, there is a controller called there are PID linear controllers. Under linear controllers, the more popular controller is PID controller. If you want to know more about PID, you want to know about deep understanding about PID control. So our Robotic Society will organize another webinar. We are planning to organize another webinar called Linear Controllers. So there we will be talking very deeply about this PID control, but here I'm going to just explain. I'm going to use a proportional control. So since the values in 0 to 1000 range, I'm going to multiply this by 0.001, and it will be in 0 to 10 range. So now I think it is okay. So now we have a proportional controller. So it is now the tuning time. So we need to tune this proportional control. Let's see how we tune. Tuning means giving right values to this constant in order to perform correctly. So let's see. Okay. Let's see how to see. We need to uncomment this speed, right? So okay, now robot is going forward, and then okay, still not great. So I'm going to move toward this side because it's taking time. And what I'm going to do is I'm going to increase this value to 3. Let's see whether 3 will do it. Okay, now it's going. Okay, barely. So let's set this value to 0.6. See, yeah. So okay. See, still not great. So I'm going to change the speed. I'm going to use a normal speed. Let's use some norm speed. Normal means norm speed. Let's set this to normal speed to 4. So say just because we can change the speed, because tuning is changing this value, every value. So tuning is very hard, but compared to other controllers, proportional control is the easiest easiest control. So let's get this camera speed. Okay, let's see now what will happen. Okay. Okay, maybe maybe this works. Okay. Uh, Okay. Hello, can you hear me? Hello.
Yes, we can hear you. Tilak.
Okay, there was a network problem. Um,
Yeah, we lost you for a second.
okay. So let's print the speed values and let's see what is happening here. Speed comma. These are novel things, but when designing robots, sometimes the code is not working. You have to deal with these things when you are designing robots. It is the new normal.
Excuse me, Dula.
Yes?
We can't see the screen.
Sorry. Uh, can you see now?
Oh,
Hello?
I can't see it.
Still?
Let's start.
Can you see now?
Yeah, we can see the screen.
Okay. Yeah. Okay, now on this one. So if I move this robot towards here, let's see what we will do. Run this. Still is our driver says run straight, go straight, and now I think it is. Okay, now let's see. He's turn left and go straight. Okay, I think driver is working fine. What is okay, now I think our robot is correctly. Let's speed up this and let's see. So that is how you create a mathematical model and put that into a code and see. So in order to run this faster, I think so our robot is running like that. So I think it can detect walls and our driver is capable of okay, now you can see there is a problem, another problem. Driver here, what happened is driver is directly at the wall. He says you need to do something. If you may remember, that happens when driver detects a wall ahead and when he does not detect any wall right side or left side. So driver is in that situation. So what we are going to do? So maybe if that situation arrives, you can write another very intelligent code that can handle these kind of things. So due to the time limitations, we are now spend 1.5 years. So what I am going to do is I'm going to say just turn right in those kind of situations. So maybe we have to save this and run home again. So let us run. So let's see what driver will do those kind of. So maybe driver go to that situation again. Sometimes. Okay. At this time it is not. I think not going to go that. So maybe somehow it will arrive those kind of situation, right? So okay. So that is how you are going to actually that is how you are going to mathematically design your object, your thing and your project robot and implement it using languages. Actually, this not not it is, does not have to be Python language. Any language you can implement using this if you have some coding language. So like that, I am going to finish this. Then and at last day, someone asked a question about can we import CAD models to the Webot simulation area, because obviously if you are familiar with CAD software, you know designing something using CAD system is very much easy, but Webot it is not a CAD software, right? It is designed to these kind of project 3D simulations. So let's see how we can import those kind of things. So in order to you can design your model using let's say SolidWorks and save the file as SRT file, SRL file. Then to import it, in order to import, highlight this robot node, go to this add thing. So under this, I'm going to add the solid. I'm going to add a wall thing, right? So I'm going to add these things, and what I'm going to do is under solid, I'm going to add a shape. So shape is the thing we are going to add, right? So I'm under solid, I'm going to add the shape. So under shape, I'm going to the geometry is the thing you are designing SolidWorks platform. So I'm going to do this geometry thing, and there we add these shapes. In previous slides we add this sphere and cylinder. Now what I'm going to add is this mesh call thing, mesh. So you can add a mesh. So go to this mesh, and here you want to give the URL. URL means file path to the SolidWorks design. So I'm going to double click on this and select. So now I have three things. This is my default file path. So in my default file path, I have inner walls, scars, and this is the monkey's face. So I'm going to add this inner wall thing. So open. So now you can see the inner wall there. So it is very much large because in SolidWorks this was defined in centimeter scale. So we need to change the scales to millimeter. So what I'm going to do is let's change this to 0.1, 0.1, and this 0.01. Oh, sorry. This is one. So you can see our model, but then so just like that you can add models, but still this is only the geometry. Now we want to add the appearance. So go to this appearance node. Let's add PBR appearance. And then let's change the metalness to 0 and roughness to 0.2. And now just like that, now what we need to define is a boundary. I think you are familiar with these things. I explained these things very well in yesterday. So go to this geometry, define this as define this as wall white, and go to this boundary object. Go to this use node and add this wall white. So we have boundary as, so you can see the boundary. So just like that you can add boundary, and I'm going to save this. So if you need this wall to fill physics, you can add, but I think adding physics is not need. So let's see whether our driver is capable of handling these kind of things. I think it may not be, but maybe our driver is not that stupid, right? Let's see. So I'm going to change this on X direction. So next direction, change, and Z direction. Okay. Okay, this is good. I'm going to save this. I'm going to rotate our robot. Let's see. No snake. Let's place this here and save this. Let's run this. Okay, it's going fine. Okay. See, okay, maybe there we get a problem. Hmm. Save this, run this. Maybe if we change the KP values to another value, it will work. Let's change it to 6. I don't know, right? Let's see what we will do. We're pretty good too. Not that intelligent, but somewhat intelligent, right? And this is okay. Somehow we managed to do this. Also, if you want, you can actually you can let's add some boxes here and there. So Control C, Control V, and I'm going to place box here. Control V, and going to rotate this and place here, and this place here, and save. Let's see. And I'm going to run faster. So I'm I think our robot is handling well. Okay, now we have arrived to a problem. So if I talk about this, I'm going to let you to decide what to do this kind of things. I have provided you the Webots software platform, and again I will send you this. Okay, when you are free, when you are when you are trying to fill the feedback thing, fill your email as well. There we can send that email, this file, that email. So also I'm going to do some things here. I'm going to these tools, and under that I'm going to go this help. There build knowledge tools. Okay, under view, you have this option called let me see where it is. I can't remember the name exactly. Optional rendering, and under optional rendering, go to this because I want to show if you show distance sensor. Now what you can see. So okay, let's run this. You can see the distance sensor rays here. So what is happening here is this object. Even though this is our driver says turn left, since this wheel is here, it is colliding with this object. It can't move. So to handle those kind of situation, you can build your robot, and there is another situation like this, let's say our these kind of situations. Okay, this is the situation. So you can see our things. Okay, now okay, so let's finish this thing, right? Okay, thank you for listening to my lecture webinar. Thank you.
Thank you very much, Arya, for that very informative session. I hope our participants could learn a lot of new things regarding the fundamental of Webot simulation and making your own robot using Webot software. So they have also sent us a few questions through the link we provided. If anyone who has missed sending the questions can now scan the QR code and send your question to us. So now I will direct those questions to Mr. Udula.
Okay.
Yeah. First question is when drawing solid, sometimes solid disappearing. Why is that?
Again, solid discipline. Maybe sometimes I think I said I especially highlight you to when you are drawing something. First, you need to go to the beginning of your. Maybe you can. I can't share my screen. Okay. So beginning to a simulation world. That means you can under that time display. Next to that time display, there is a button called go to the beginning. Press that. Then after that, then go to the beginning of the simulation file, beginning of your world, and then start to draw build something. And after that, save it and then run it. I think if you follow this method, you can handle that situation.
Thank you, Aya. So the next question is, I would like to know how we can learn how to build a real robot, how we can gather the knowledge, any references, please.
References. Actually, building a real robot is not this much easy. You have to deal with the things like sometimes the environment is changing. You have to think about how these variations will have affect our robot. Let's say here we are going to use IR sensor, but in the real world, our sun is a great IR source. So sun is emitting IR rays. So we need to deal that IR rays as well. So those things are there. So if you want to start building robots, so I recommend you to use Arduino because even though Arduino is a very prototype oriented board, in Arduino you have many resources. In internet, you can go to the Arduino page. There you have another section called projects, Arduino projects. You can go to that project section and there you have project codes and where to order these devices, everything you have there. It is a great source. And some YouTube videos, there are good videos, some videos are bad, but there are some videos which explain the program line by line. I recommend you to watch those kind of videos where the programmer is explaining everything. But don't do this thing, right? Build your what do you call the hardware part and go to internet, copy the relevant code from internet and paste it. Don't do this. Please try to write your own codes. That will help you a lot when you are designing not actually robot, even when you are writing some programs to any other thing study, when you are writing any program for your study materials, that experience will help you. Thank you.
Okay, thank you, Aya. So the next question is, can we simulate a particle swarm optimization algorithm in this?
Yeah, actually you can. And Webot has built-in swarm robotic environment. Okay, after this Q&A session, I will show you that part as well. Yeah, you can build. Also, you have a built-in swarm robot platform as well.
Okay, thank you. So the next one is it possible to make multiple agents and make them communicate? What are the things I have to look up for to get this done?
Yeah, it is possible. Actually, Swarm Robotics is that you connect make connections with many robots and do they communicate together and do the task together. So you can use that. In that case, you can build let's say three robots. You have to build three robots, and then you can run three controller codes to each robot, and you can run that code as well. So the transmitting part will handled by Webot, so you can't use any Bluetooth or any other that kind of sensors. But actually, you can build those kind of stuff, robots as well.
Thank you very much, Aya. With that question, the Q&A session is concluded. The recording of today's session can be obtained using our YouTube channel, and also the final code and the presentation will be shared among everyone who fills the feedback. You can now access the feedback through the link we displayed then in the chat box, and also you can scan the QR code and access the feedback form.
Okay, actually, we can send this Webot file as well.
Yeah.
Presentation.
So with that reminder, we have almost arrived at the end of today's session. On behalf of our society, I would like to thank Mr. Udula for joining with us today. Mr. Udula, please accept our token of appreciation presented to you by the Robotic and Automation Society of University of Peradeniya. Finally, I would like to thank all the members and all the participants for joining with us today. This marks the end of phase 1 of Robotics 2022. Soon we will share a small robotic task for you to complete and submit. For those who complete the task and submit, will receive a valuable certificate. Now it is time to conclude this webinar. Hoping to meet you all at the second phase of Robotics webinar series. Stay safe everyone and have a good night. Thank you.